Greetings to everyone and welcome. Many thanks for joining us today for these presentations. I'm presenting the collaborative work with USB on FSI of wind turbine blade and assessment of Nektar++, SHARPy and OpenFOAM CalculiX solver. Mr. Rodolfo Piuraca and I, Mosa Lauti, will present this work to you, and I'd like to acknowledge the involvement and help of Dr. Bruno Carmo, Professor Rafael Palacios, and Spencer Sherwin on this work that I'm presenting on behalf of them as well. As I mentioned, this is a collaborative work with USB. We're developing two different geometrically resolved FSI solvers for FSI simulation of wind turbine blades, with using different fidelity for both fluid and solid modeling. Therefore, we took this opportunity to have an assessment on effect of fidelity, like LES and URAN's approaches on predicted aerodynamic forces, effect of quasi 3D versus the full 3D approach that we're using in fluid simulation, effect of a structural modeling approach on predicted structural deformation, and we will have a comparison on the scalability and providing guidelines on the applicability of each approaches. I have to mention that these are the general and overall objective of this collaboration. This is a work in progress, and we will update you on the progress and where we get till now, and show you whatever we get from these collaborative objectives. On the physical perspective, as the wind turbines grow, the modern wind turbines grows in size to increase the individual power output of each turbine. They uses a large flexible blades. Therefore, we need tools for efficient, high fidelity FSI simulation for simulating such blades. And high fidelity here is in contrast to the commonly used low fidelity potential based approaches. We need FSI tools to have a realistic simulation of highly deformable slender structures, high Reynolds number flows, and largely separated flows, which has application in wings install and also wind turbine blades in park condition, which is a new design criteria for modern long blade wind turbines. The challenges we're facing that in such conditions, we have huge separated flows, which features a thick boundary layer, leading and trailing edges separation, and vortex shedding, which can interact with the leading trailing edge separation. Of course, if the wind is moving, like in the case of VIV, vortex-induced vibration, we will have the flow would develop anisotropic turbulence, which definitely needs high fidelity simulations such as LES and DNS method. RANS is not that appropriate in that part, but still can gives us a estimation of what we can expect there. Another thing is that we have a very high Reynolds flow over the wind turbine blade. To have, for example, if we want to have a DNS simulation, such a simulation will have the grid resolution will decrease as the Reynolds increase, and therefore the flops scales as Reynolds to 3. This shows how much computational resources that we need to have a efficient flow simulation over a slender structure. Therefore, we need to have efficient numerical method, no matter if you're using the LES or the URANS approaches, and the code must be highly scalable. The scalability is an issue here. So let's have a overview of the two solvers. At ICL, we are developing an FSI based on the coupling between Nektar++ and SHARPy. I will call it ICL solver for simplicity. And at USB, they're using OpenFOAM CalculX coupling for the FSI solver. The ICL solver uses the LES method, very high fidelity approach for fluid simulation, while the USB uses the medium one, URANS. On the other hand, we are using quasi 3D approach, thick strip method for representing the fluid domain, while the USB uses the full 3D approach. We're using high-order spectral method versus the second-order finite volume method. Our approach uses the beam model to represent the slender structure, while the USP uses the full FEM modeling for the structure, and both solvers support nonlinear structural modeling, and both of them are open source and freely available. For Nektar++, let's have a look at Nektar++ solver, and then I hand over to Rodolfo to talk about the CalculiX, and then come back to you for the conclusion. For the Nektar++, because we're using a high fidelity approach, large simulation, and the flow is and the blade is very slender, it's practically impossible to have the required resolution for such simulation. To overcome this problem, we represent the 3D domain as we model the 3D domain as a separate, smaller domain, each of them called thick strip. Each of these strips has a span-wise length in LZ, as you can see in the figure. This span-wise thickness enables us to capture the local 3D turbulence. Therefore, we are able to capture the local three-dimensionality of the flow. And because we're not representing the full 3D domain over the slender structure, it reduces the computational cost, since we are able to have a high fidelity simulation for such a problem. The strips are not directly connected to each other, but via the via the dynamic of the structure. And we're using the high order element in XY domains, as you can see, a representative of high order element that we're using, and the Fourier expansion for discretization of the domain in the span-wise direction. The numerical method for the flow solver, we're using the transform Navier-Stokes equation. We're transforming the coordinates to avoid the remeshing because of the high deformation of the structure. The equation are discretized with high-order spectral element method, p-order polynomial expansion in XY, and Fourier in Z direction, and the high-order stiffly stable velocity displacement coupling for velocity correction scheme. The flow solver is implemented in Nektar++. On the other hand, for the structural solver, the beam is modeled as a the blade is modeled as a beam because it's a very slender structure. We use geometrically exact composite beam model, nonlinear high deformation with support for static and dynamic formulation, quadratic finite element method, and Newmark beta time equation. These are implemented in SHARPy, and we couple these two solvers together to have the FSI solver for our simulations. The problem that we're going to talk about today is a standard problem of hail wing deformation. It's very similar to a blade, but to avoid the complexity of the blade span changes, the changes of the span, the airfoil section over the span and the twist and everything. On our assessment of the solvers, we choose for our first example a rectangular blade, which means it has a constant airfoil over the blade. You can see in the figure how Nektar++ SHARPy solver represent the flow. It uses here 8 strips to represent the flow domain, and we have the full structure as a slender beam here. On the figure B, you can see the flow configuration in XY domain, which we have a flow with the angle of attack. The Reynolds number considered here is 156,000, and it's comparable to a real turbine blade, which is of order of 1 million. So on the flow physics, it gives the required feature for us. Now, for a fixed airfoil section, let's have a comparison between the aerodynamic prediction of the forces between Nektar++ and OpenFOAM. You can see the lift coefficient, drag coefficient, and moment coefficient over a range of angle of attack from 2 to 20 degrees. The black line is the Nektar++ results. The green one is the OpenFOAM, and the other two are the experimental data. In most of the angle of attacks, we have a very nice agreement with the experiments. However, near the stall region, on the onset of the stall region, about angle of attack 11, 12, the LES simulation have a little bit over prediction for the lift coefficient, which is the most important coefficient for us here, because that's the driving force of the blade to deform. And this is mainly due to the cleanness of the flow. Flow is too clean compared to the other approaches because of the high resolution and high fidelity. The incoming flow need to have some disturbance that we're working to improve the result also. Interestingly, for the moment coefficient, which also have effect on the structural deformation, Nektar++ prediction is both solvers have a little difference on the large angle of attack where we are in a deep stall. We are predicting lower values, while the OpenFOAM predicted higher values compared to that experimental data. Generally, we have a good agreement with the experiments, and we can rely on our results. As a first example, we considered a flow with angle of attack 4 degrees without considering the gravity forces, same Reynolds number. You can see a comparison of the prediction of the deformation from the Nektar++ simulation with two other approaches. The blue one is using the beam. All three of these approaches use the beam as the representative of the slender structure. However, the blue one uses the UVLM potential-based method, unsteady vortex lattice method, to predict the aerodynamic forces. The other one is a medium fidelity using the inviscid flow solver to predict the aero forces. And because of the difference between the fidelity of the flow solvers here, both two low and medium fidelities have a little bit difference in their prediction. And of course, we also have a different small difference at the tip of the domain, tip of the blade, because of actually the prediction and the resolution that we're using. An important thing is that because of the thick strip approach that we're using here, we are able to capture the local three-dimensionality of the flow, but since the strips are not directly connected to each other, we're not able to capture the global three-dimensionality. Means we're not seeing the tip effect, which reduces the lift force, the driving upward force near the tip. To overcome this, in our simulation, we used a profile function, tip loss correction function, as in a form of Prandtl tip loss function, as you can see, and fit it over the UVLM data to get that three-dimensionality effect. However, now we're working on extending this approach to have a more naturally embedded approach, not using the predefined function, using the vorticity of the domain to correct and include the global three-dimensionality. I'm not going to talk about this today, and hopefully we'll update you on that on another presentation. For another problem, the same case with a small angle of attack 4 degrees, but this time we include the gravity and the comparison with the UVLM solver, as you can see on the left figure. On the right figure is the local angle of attack that each section of the blade is see in each of the strips. As you can see, moving toward the tip from the root on strip number 1 to strip number 8, which is located at the tip, the local angle of attack increased. So as the wing moves upward, also it rotated, and the flow become more separated compared to the one that near the tip, which increased the lift coefficient and of course have an impact on the deformation. Nevertheless, this is a small angle of attack, and we get the our prediction of the deformation is very close to the low fidelity UVLM solver, which is expected because they will have a good approximation in that low angle of attack. However, as the angle of attack increases to a large value and the wing goes into the stall region, like this simulation that you can see here with the incoming flow of angle of attack 16, that might happen in the park condition. Even in the park condition, we will face angle of attacks near 90 degree. So it's a massively separated flow. The low fidelity solvers like the potential base are not be able to capture the flow physics correctly because of the large separation that haven't been seen in their formulation. You can see the distribution of the strips and the huge separation over the wing and also the deformation. The contours are Q isocontour, which is colored with the velocity between 0 to 2 meters per second. Now I'm handing over to Rodolfo to talk about the OpenFOAM CalculiX, but I will have a control on the slides. Rodolfo, please.
Hi, I am Rodolfo Buraca, and I represent the OpenFOAM and Calculix FSI coupling. Next slide, please.
Yep.
OpenFOAM is a finite volume solver and solves the part of the fluid dynamics in the hail wing problem. We are using Pimple FOAM set in the piezo solver mode and using Uran's turbulence, K omega SST, and the second order backward time scheme. Being the 5 times 10 to the power of minus 5 seconds, the simulation time step. Next slide, please. CalculiX is a finite element solver solving the structural part of the wing. In the problem in the question, we are using a dynamic nonlinear model using the solver spools with orthotropic material and fixed time step of also 5 times 10 to the power of minus 5 seconds, making the both solvers have the same time step. So the coupling has the characteristic to do not have subcycles in the fluid dynamic part. Next slide. The program that makes the coupling between OpenFOAM and CalculiX is precise, being a program that has data communication libraries between the solvers. It's necessary to make 2 programs, one for the structural and another for the fluid solver. Called adapter is the green part of the graph. To connect the both solvers with precise, so that one does not need to know that the other solver exists, executing each one independently. Precise allows serial and parallel coupling, being the first used in this work, where the fluid solver is always executed before the structural solver and repeat in that sequence. The mapping is done between the fluid and structural solver, where the fluid data of the pressure in the center of the cell is mapped to a pressure in the nodes of the structural solver elements, and the displacement of the nodes of the structural solver elements are mapped to the center of the fluid solver cell, using the nearest distance mapping. Next slide. The mechanical properties of the wing are shown here, where there are different stiffness in the flapwise and chordwise directions. So we use in the CalculiX orthotropic elastic material, which the model characterized for transversal isotropic elasticity, where the elasticity, Poisson and torsion modules are divided in two planes, the plane and the tangential variables. Next slide. First, the flexibility matrix was made with the calculation of the mechanical properties so that the stability relationships are respected in order to the solution do not diverge. Then the stiffness matrix was calculated by making the inverse matrix of the flexibility and placed as an input in the CalculiX material. Next slide, please. Here we show the OpenFOAM mesh, which has the same dimensions as the sections used in the Nektar simulations, but in the z directions has a length of 30 chords and a distance between the tip of the wing to the wall of the mesh of 14 chord. And this is because we model the 3D full 3D dimension wing. The first layer has 1 millimeter high with a grow rate of 1.1, resulting in a Y plus of 100. And the mesh has in total 9.1 million cells. Next slide. Here is showed the structural mesh, which has brick and wedge quadratic elements, totaling 2,976 elements. We also show the results of displacement test and beside the comparison with the analytical displacement versus the wing length, which shows a good agreement for a small force applied. Next. On this slide is show the result on the rigid wing with a high angle of attack of 12 degrees and used for testing the mesh of three-dimensional fluid dynamic part, and which will be used for initializing the FSI simulation. We can show the video now.
Yeah, let me. I couldn't end the video here, but I have it. So this is.
All right. Here we show the evolution of the structures of the key criterion of 20 colored by vorticity and the formation of the structure at the wingtip.
Yeah, but the flow is still at earlier stages, so I need to.
Yes.
Okay, next slide.
Yeah. Finally, the initial result of FSI simulation is shown for a low angle of attack of 4 degrees. The video will be quite fast as these are initial results.
Okay, let me play that video while you're explaining what happened.
But there are interesting physics observed in the video, such as a greater deflection in the middle span and a deflection reduction in the wingtip due to the reduction of the lift force caused to the wingtip vortex. As the simulation progresses, we may see a little different wing deflection in this part, which will be interesting to compare the results.
Now, this is actually the tip effect, because the lift goes near zero at the tip, so it deflected a little smaller than the inner part of the blade. Okay, shall we go to the next slide?
Yes.
Okay. Thanks, Rodolfo, for explaining the OpenFOAM CalculiX solver. Before I continue, I need to mention here that there are a couple of things. Their simulation, unfortunately, wasn't ready to compare the result with our results. So this is the initial stage that you have seen here, and it's still running. Hopefully we get a very good result, and we will be able to compare for a full range of angle of attacks and various conditions. Okay, so let me have an overview of the solvers that we are developed here. The Nektar++ solver use the resolve turbulences, is able to resolve the turbulence structure, capture the anisotropic turbulence, which is good for VIV prediction, but our solver is restricted to beam modeling. The quasi 3D, we're using the quasi 3D for flow field, using the sections to be able to have the high resolution. The solver is highly scalable, but because of the LES approach for fluid, is it has a high computational cost. Using these, we are enabling to have an FSI LES, hopefully DNS simulation of various slender structure, and this is suited for moving a structure with massively separated flows. On the other hand, the OpenFOAM CalculiX uses the RANS modeling, which is more suitable for capturing isotropic turbulence, because the CalculiX uses the 3D FEM, not using the beam modeling. And as you have seen, they have lots of problem to represent the beam structural parameters to fit to CalculiX to have the same structural behavior. Those slides that Rodolfo presented to you, and they have spend a lot of time to get the correct numbers that work for both of us. But still, they can have other various form of solids because of their solid solver. They use the full 3D domain, full 3D flow field, so they don't have the tip problem that we have here. The scalability test, they have a good scalability, but still they're working on that one. They have some also problem on the precise and the coupling between the solvers on the parallelism part. They're working on that part. Is still in progress. That's why we didn't show any scalability test comparison here. They have the lower computational cost compared to Nektar++ SHARPy. It's more suited for medium range design in industry, and suited for the structures with low flow separations because of the RANS modeling. Our future steps of this collaboration consist of finishing this work and having a comparison of the scalability of the two solver. We did that for the Nektar++. We're waiting for the USB to finish their test for the OpenFOAM CalculiX. We're extending this work for the NREL 5 megawatt blade, and then having a test for the VIV of the blade in part condition. And finally, we will provide the detail on when each of these solvers are more appropriate to be used. Basically, the OpenFOAM CalculiX will be more appropriate for the day-to-day design in industry because of the lower cost, but for final stage of design, and especially in park condition, when you have a very high separation of the flow, the Nektar++ is a more suited choice. The outcome of this collaboration is 2 conference paper, and one submitted to WESC 21 and one to COBEM 21. We will have the WESC in a month, and the COBEM will be in November. And we also organize the mini symposium, Advances in High Performance Computing for Wind Energy Application, in collaboration with USP at WESC. For the conclusion, two FSI solvers, geometric results are developed for high deformable slender structure. Each targeted a specific range of application. Both needs exascale, even if the RANS calculation is cheaper than FSI than LES. However, because of the slenderness of the body and their 3D approach, is still very computationally expensive, and both needs to be at least exascale comparable. Comparison on the aerodynamic were presented, and the work is in progress for comparison of the deformation and extension for the NREL blade. We will be happy to have your questions. Thank you very much.